So last time around, we looked at interactive programming in Haskell. And in particular, we looked at how to do simple text-based input-output. So what we're going to do today is a couple of things. We're going to kick things off with a quick review of what we did last time around, a quick review about how you do I/O in Haskell. And then what we're going to be spending most of our time doing today is a live coding exercise. And actually what we're going to be doing is solving the exercise from the last lecture, which is to implement the game of nim. But before we get started with this live coding, I'd like to just kind of reflect on the problem which the I/O mechanism in Haskell solves, and then how it actually solves it. So the problem is illustrated by these two basic sentences here. So the first observation, or the first statement, is that Haskell programs are pure functions. And what I mean by that is they're pure mathematical functions. All they do is take an input, process it silently without interacting with the outside world in any way, and then finally they're going to deliver an output. So they simply take an input, process it in some way, and then deliver an output. And then the second statement is where the tension arises. If you want to write interactive programs, such as games for example, you need to have side effects. You need to interact with the outside world. So we see here we have a tension. Haskell is a pure functional language, so the programs are pure mathematical functions, but in order to write real interactive programs, we have to deal with the issue that the real world involves having side effects. So the way this is actually handled in Haskell is we simply are going to use types to keep a clean separation between the two worlds that we're interested in. So we're interested in programming primarily in Haskell with pure expressions. So these are things which do not have side effects. But we also need to deal with the real world. So we're also going to need to deal with what in Haskell is called impure actions. And these are things which can have side effects. So the idea is that we're going to leverage the fact that Haskell has a very nice type system to keep a clean separation between the pure expressions and the impure actions which may have side effects. So how does this actually get realized in practice? So in practice, what you have is a type of so-called actions. And that's this type in here, highlighted it in yellow. So the type I/O of A, this is impure actions that eventually will return you a value of type A. And the idea is that if you have a program of type I/O of A, it may interact with the outside world. So it may read characters from the keyboard, it may print things on the screen, it may interact with the file system and so on. So it can be an impure action, but eventually, once it's finished, it's going to give you back a normal value of type A. So for example, if I had a program of type I/O of int, then it would interact, or it could interact with the outside world, but eventually it would deliver me an integer. So in order to program with impure actions of type I/O of A, the Haskell system provides us with a number of primitives. So we'll very quickly review the primitives for doing simple text-based input-output. So what we learned about first of all last time is there is a primitive called getChar, and it does exactly as its name suggests. It's going to read a character from the keyboard and give it you back. So it's going to be an action because it needs to interact with the outside world, and its result value will be a character. And again, the important point here is this I/O tag. If we simply said that getChar had type char, all it could be was a constant, like returning the character A. If you wanted to actually be an impure action and have the side effect of reading a character from the keyboard, we need to have the I/O tag on its type to indicate that. And then of course what we had was the dual function called putChar. And what putChar does is you give it a character as input, and it's going to give you back an action which is going to print that character on the screen. And notice here that this is a purely side effecting action you're going to get back, because we have the void result type here, because when you print a character on the screen, that's always going to succeed, so you don't need to return any meaningful result value, but you still need to return one. So here we're returning the void result value, which is simply the empty tuple. And then finally, what we learned about last time is that you need a little function called return. And what return is going to do is it's going to convert values of type A into impure actions of type IO of A. And what it's basically going to do is take a value like 5, and it would build you an action which doesn't interact with the outside world at all and just simply returns the input that you gave it, like 5. So return 5, for example, wouldn't interact with the outside world. It would just immediately give you back the result value 5. And the way we think about this is it's kind of like a bridge between the pure world of values of type A and the impure world of values of type IO of A. And as we saw last day, then you need actually to use this return function quite a lot when you're actually writing interactive programs. So we can actually illustrate this with a little picture. If I imagine the pure world of regular Haskell programs or values of type A on the left-hand side, and then we have the impure world of side effecting computations, which have type IO of A on the right-hand side. So the pure world is the values of type A over here, and the impure world is the values of type IO of A over here. What return is giving you is a little bridge. It's allowing you to go from the pure world over to the impure world. And crucially, as we learned last time around, there is no bridge back. Well, actually, there is a bridge back, but that's really for internal use within the compiler. If you're a regular Haskell programmer, you're allowed to go from the pure world into the impure world via the return function, but you're not allowed to go back. So that's it for the 3 basic primitives. And then what we saw last time is that using these 3 primitives, you can actually bootstrap or derive a number of other useful library functions. So let me show you a few of these again, because we'll be using these today when we do our live coding. So the first thing we bootstrapped last time is we defined a little function called getLine, or a little primitive called getLine. And what getLine does is it simply reads a string of characters from the keyboard. And it's defined recursively by repeatedly calling getChar until someone types the empty, or someone hits the return key at the end. Then we had the dual primitive, which is called putster, and it takes a string as an input, and it converts it or gives you back an action which simply prints all those characters in the string on the screen. And again, this is defined using recursion in terms of the putchar primitive. And then finally, we sometimes need another little primitive, which again is built into the standard library. It's called putsterline, and it takes a string as an input, and it's simply going to print it on the screen. But this time around, the ln part on the end of its name tells us that we're going to take a new line as well. So it's simply going to admit a return character to move on to a new line. So the only other thing you need once you have these basic primitives, so you've got getChar, putchar, and return, and then you've got a number of derived primitives like the one on the screen here, is you need a way of sequencing actions together. And this is the do notation, which we saw last time around. And we'll see that illustrated quite a bit today when we come to implement the game of nim. But basically, these 6 primitives, which I've shown you, is all that you really need for doing basic text-based input-output, and it's all that we'll need for doing the nim game in a moment. So before we come to do that, I'd just like to make one final comment. We're just looking at simple text-based input-output here, but of course Haskell can do much more sophisticated things. It can do file handling, graphics, windows, sound, and so on. And all of those things are handled in a very similar manner by using the IO type to keep a clean separation between the world of pure computations and the world of impure computations. But we're not going to look at that in this course. So what I'm going to do now is move over to the Glasgow Haskell compiler and introduce you to the NIM game, and then we'll see how we can actually implement it by doing a kind of live coding session. So what I'd like to do first is give you a quick demo of the game that we're going to be writing to make sure that everyone understands what the game is about and what the rules are. So I'll load it into the system. So GHCI nim.hs, we're writing the game of NIM, and there's no errors when I load it in, which is good. And then I can start the game. And what you see is it's a simple board game played with a row or rows of 5 stars. So we have a board where in the first row we have 5 stars, in the second row we have 4 stars, and then so on down the board. And if you're familiar with the NIM game, there's various different configurations of the initial board. It may be larger than this, it may be smaller. The stars may be arranged in different ways, but the basic rules of the game are always the same. So there are 2 players, and they take it in turn to remove as many stars as they like from the end of a single row. And they take it in turns doing that, and then the way that you actually win the game is if you are the player that makes the board empty, then you win. So if you remove the final star or stars from the board, then you are the winner. So we could have a little game with this. So if I was player number 1, I may say in row number 2, I want to remove 3 stars. And you see now there's only 1 star left in row number 2, and then player 2 may say in row number 1, I want to remove all the stars, and the game goes on, and you play like this, and you compete against each other, and you try and figure out what a winning strategy is, and eventually it gets down to the point where one player makes the board empty. So I'm player 2 here now, and I can go play in row number 5, remove the final star, and I am the winner. So it's not a particularly interesting game, but it's a good example for illustrating how to write simple interactive programs in a language like Haskell. So what we're going to be doing is implementing this in what's called a bottom-up manner. So this is in contrast to how we did the Hangman game in the last class. There we came at it in a top-down manner. We wrote the top-level program first, and then we defined little functions that we needed for that later on. Here we're going to come at the problem in the opposite direction. We're going to come at it in a bottom-up manner. We're going to implement little utility functions or helper functions, which will then combine to actually implement the whole game. What we'll see is that the code we're going to write today is just over 1 page of code, so it's a bit bigger than most of the programs we've been writing in the course so far, but it actually brings together everything that we have done in the course. So we're going to be using list comprehensions, we're going to be using recursion, we're going to be using higher order functions, and of course we're also going to be using simple input-output. So to kick things off with implementing the game, what I'm going to do is start up a text editor, and here I've got a blank file called nim.hs, and this is where I'm going to write my code. So the first thing I'm going to do is I'm actually going to import a very useful standard library which is called data.char. And what data.char contains is a bunch of utility functions to do with characters. And we'll be using a couple of these today, and I'll point these out to you when we actually use them. So I'm going to make a little comment here. The first thing we're going to do now is to define a bunch of utility functions on the NIM board. As we mentioned a few moments ago, we're going to come at this problem in a bottom-up manner. We're going to implement a bunch of utility functions, and then we'll use those to define the actual game later on. So the first thing we're going to do is declare a new type which represents the board. And the idea is going to be very simple. A NIM board is simply going to be a list of integers, and it's simply the number of stars which you have left on each row. So we could have a really simple example of this. We could have the initial board, and the initial has type board, and we could just simply say initial is 5, 4, 3, 2, 1. So we see the idea here. A board is going to be a list of integers, and here is an example board. This is the initial board where you have 5 stars in the first row, 4 stars in the second row, and so on and so on. So at this point, I have typed in a bunch of definitions. So let me save my file, and then I can go down to the bottom here and actually try loading it into GHCI. So I can type GHCI nim.hs, and it loads in, and we get OK down at the bottom. So everything is loaded OK, and that's great. So for example, I could say, what's the value of initial? And it's exactly as we expect. It's 5, 4, 3, 2, 1. So the next little helper function I'm going to write is, it's going to be called finished. And what finished does is you give it a board as an input, and it's going to tell you, has the game finished at this point? So it's going to give you back a Boolean, either true or false. And it's very easy to decide if the game has finished. If you take a board such as this one, if all the numbers in the list are 0, that means there's no stars left on any of the rows, and therefore the game is finished. So how could you check if all of the values in a list are actually 0? Well, there's a very useful library function we could use here. We could use the all function. And what all does is it takes a property, such as being equal to 0, and it takes a list of things, such as the board, and it just checks, are all of the things in that list, in this case, equal to 0. So again, all is a higher order function, because it's taking a property here, which either returns true or false, and then it takes a list of things, which here is the board B, and it applies the first thing to the second thing all the way across and checks, do all the numbers in that list actually equal 0? So I could save this again, and I could reload it down here and check to see, does this actually work? So if I said, is the initial board, let me just type it in manually here so you can see it, is the initial board 5, 4, 3, 2, 1 finished? Well, the answer is no, because it doesn't contain all zeros. Whereas if I said, is the board which just contained 5 zeros, is that finished? Then the answer is true, because all of the entries in the board actually are 0, as we can see. So that's another little helper function. There's 2 more little helper functions on boards which I want to define. So the first one is going to decide for us if a move is actually valid. So I'm going to take the current board as an input, and then I'm going to take the row number which the player wishes to play on. Then I'm going to take how many stars they wish to remove from that row, and then I'm going to finally give back true or false, depending on whether that move is actually valid. And this is a really simple function to define. All I'm going to do is take the board B, the row number row, the number of stars which they wish to remove, and all I need to do is index into the list at the appropriate position and see, is there sufficient stars at that position. And the only trick is, if I was playing on row number 1 and I wanted to see, is it valid to remove 4 stars from row number 1, this is the number here at index 0 in the list, even though it's row number 1. So the only tricky part, or the only part you need to watch out for, is when you index into the list, using the indexing operator, bang bang, you need to remember to subtract 1 from the row, because row counting for us started at 1. We had row 1, 2, 3, 4, 5, whereas when you index into a list, such as this one, you have index 0, 1, 2, 3, and 4. Okay, so you subtract 1 from the row, and then all you need to do down here is check, is the number which you find there bigger or less or greater than or equal to the number of stars you're trying to remove. So a nice simple one-line definition. Again, we could try it out. If I reload the program, it's fine. And I say, if I want to play with this board here, and I'm playing in row number 1, and I want to remove 4 stars, that's okay. Whereas if I did the same thing, 5, 4, 3, 2, 1, row number 1, and 6 stars, that is not okay, because I do not have 6 stars in the first row. So again, nice, easy, one-line function definition. So the final function, which I'm going to implement on boards, is probably the one you are most expecting. It's the one that actually makes a move. So the move function is going to take a board, it's going to take a row number, how many stars you wish to remove, and then it's going to build you the resulting board. And this function is going to assume that you only apply it with valid moves, so we'll assume that someone has already checked, is the move actually valid? So we don't need to build any error checking actually into the move function. So let me actually give you the definition. So you take a board B, you take a row number, you take how many stars you'd like to remove, and then I'm going to define this using a little list comprehension. So let me write the definition, and then I'll explain how it's all working, because there's a few components to understand. So there's the list comprehension, and then I'm going to have a where I have a little helper function called adjust. I'll define this. It's just a simple conditional, and I'll save that there. So there's the definition. How does it actually work? So we're taking a board B. This is the row number. This is how many stars we wish to remove. And then what we're doing is we're building a new board over here by using a list comprehension. And what the list comprehension is doing, first of all, is it's zipping the row numbers with the board entries. So what this is going to do is we have the list 1 to 5 here, and we're going to zip it with the board. So remember what zip does is it pairs up the corresponding elements. So we'll pair up 1 with the first element of B, 2 with the second element of B, 3 with the third element of B, and so on. So when we select these pairs R, N, R is going to be a row number, 1, 2, 3, 4, 5, and N will be how many stars are left in that particular row, because that's coming from the second component of the zip. So all we're going to do then is for each of those pairs of a row number and how many stars are left in that row, we're going to call a little local helper function called adjust. And all adjust is going to do is check, is the row number, which we're currently looking at, the one we wish to remove stars from? If it is, we're going to actually subtract the number of stars which the player has input over here. So we take the number of stars currently in the row and we subtract the number of stars the player wishes to remove. And if it's not the row, so if it's not the row we're actually looking for, we'll just leave the number of stars alone. So this is the only function in today's class where maybe you need to think a little bit about what's going on. Everything else is either a one-liner, like we see up here with valid and finished and so on, or it's actually going to be quite a simple function that is just going to do some simple I/O type stuff. So we've saved this. Let's just save it again. Let's just check it actually works. So it loads fine, which is always good. So let's try applying the move function. Let's try the board 5, 4, 3, 2, 1. And we're going to play in row number 1, and we want to remove 4 stars. And we see it's done the right job here. We have 5 stars in the first row. We've removed 4 of them, and down here we only have 1 star left. And all of the other numbers have been left alone because that's exactly what the adjust function does. So let's try one more example. Let's try moving 5, 4, 3, 2, 1. And let's play in row number 3, and we want to remove all the stars. And you see here, we had 3 stars here. We've removed them all, and we've got 0. So there's one more little thing to talk about with this function. You might like to try implementing this function yourself in a different way. So I've used a list comprehension over here. You might like to do it with a map rather than a list comprehension, because we're essentially just mapping the adjust function here, except it's working on, it's a curried function here, but rather than taking inputs as a pair. But if you think about it a bit, you can define this function using a map. And if you think about it a bit, you can also define it using take and drop as well. So a little exercise for you, try and redefine the move function for yourself in other ways. So the next thing I'm going to do now is I'm going to define some utility functions or utility definitions to do with I/O. So I'll put another little comment in. I'm going to define some input-output utilities which I will use when I define the final version of the NIM game. So let me make a bit of space first of all. So the first thing I'm going to do is make a little helper definition that just moves onto a new line. So this is going to be an interactive program or an interactive definition. So I have the IO tag in here, and it's going to be purely interactive. So I'm simply returning the void result value. And the way I define new line is entirely straightforward. I just call the putchar primitive, and I omit the \n, which is the right character to move on to the next line. So let me save that, make sure everything's okay, which it is, that's good. The next function I'm going to define is going to build me a string of stars. So I give it an integer, like 5, and I want it to build me a string of 5 stars. And the way I'm going to do this is very, very easy. I take the number n as an input, like 5, and it's going to be a nice simple Haskell one-liner. Here is how I'm going to define stars. So what stars is doing is I'm using a library function called replicate, which is very useful. You give it a number like 5, and you give it a thing. In this case, I've given it a string, which has a star and then a space, and it builds you a list with that many copies of the thing. So in this case, I might replicate the string 5 times. And then that's going to give me a list of lists, and I can concatenate that to give a single list just by using the library function called concat. So if I save this one, and I can test it out down below, make sure always to remember to reload. Yep, reload's okay. So if I say, please give me a string comprising 5 stars, then you see that's exactly what you get down here. So very, very straightforward. And the reason I've defined this is I now want to define a function called putRow, and that's going to display a single row on the screen. So what I'm going to do is I'm going to give it the current row number, or the row number I wish to display, how many stars is left in that row, and then it's going to print that row for me. So it's going to be a purely interactive result which doesn't give back any result value. You just execute it for its side effects. So how do I actually implement this? Well, this is again very easy. You tell me which row you're on, you tell me how many stars is on that row, and then I'm going to do a bunch of actions. And remember, the do notation is the way that you can sequence a bunch of impure actions in Haskell. So what I'm going to do is I'm going to emit a string, so I'll call putStar, and I'm going to simply emit the row number first, and I need to remember to convert that to a string. So row is an integer. Show will convert almost anything into a string, so it's very easy to convert an integer into a string, and then putStar will put that string onto the screen. Then in the second line, what I'm going to do is I'm just going to omit a colon, just to have a little bit of space here, and then in the final line here, I'm going to put star ln, which moves on to the next line, stars of num. And that will emit, that will print the number of stars which is actually on the row. So if I save this and I load it in down here, loads fine. And if, for example, now I could say if I put row number 1 with 5 stars, then it's going to print me that row. So you see here we have the row number at the start, we have a colon, and then we have the number of stars. So the next helper function I'm going to define is actually going to do the same thing, but display an entire board. So it's going to take a board as an input, and it's going to print it on the screen. So we need to have the IO tag in here. And the way I'm going to define putBoard is actually very, very simple. I'm going to say if I've got a board with 5 rows in it, A, B, C, D, E, so that's the number of stars in each of the rows, all I'm going to do is put the rows one at a time. So I'll display row number 1, then I will display row number 2, and let me just copy here and then change so it's a bit quicker to type. So row 4 is D, and row 5 is E. So this is not nice code. You're probably looking at this and thinking, well, this is a bit of a hack. This only works if I give it a list of 5 numbers. It is a hack, but I've just kept it nice and simple here. And I'll leave it as an exercise for you to try and write a more or a nicer version of the board function which works for a board of any size, rather than just kind of hacking it here by manually printing out these things one at a time. But I'll leave this as a simple piece of code here. Let me load it in and try that it works, or check that it works. Let's try printing the initial board. And oops, I don't think I've loaded it in properly. Let me put board initial, and it's now printed the initial board for us here. So we see we have exactly what we'd expect, 5 stars down to 1 star. Okay, so just one more little IO utility function to implement, and that's going to be one that reads a digit from the keyboard. So we're going to declare a function called, or define a function called getDigit. And what getDigit is going to do is it's going to take a prompt, and the reason we're taking a prompt here is there's 2 different ways we're going to be reading a digit. We're going to say how many or which row do you wish to play on, so that's going to be one prompt, and how many stars do you wish to remove from that row, and that's going to be a second prompt. Okay, so we'll pass the prompt as an input to the function, and what it's going to give you back is an action which is going to eventually give you back the integer digit that the user has input. So how are we going to define this? So I'll make a bit of space because there's a few lines involved with this definition. So I'll say getDigit, and then you take your prompt as an input, which is just a string, and then I'm going to do a bunch of things. So first of all, what I'm going to do is emit the prompt so the user knows what they are expected to input. So I'll just display the prompt on the screen. Then I'm going to read a single character from the keyboard, and I'll call that character X. And at this point, I'm going to use one of my little helpers. I'm going to call new line to just kind of move on to the new line so that things are laid out quite clearly for the user. And then I'm going to do a test. So I'm going to test, is the character that they have actually typed in actually a digit? So isDigit here takes a character like X and it returns true if it's a single digit, so between 0 and 9, and it returns false otherwise. And this is one of these little helper functions that's defined in the data.char library. So if we actually have a digit, then what we're going to do in the next line is we're going to return it, and we need to remember to convert it actually into an integer. So I'll use another little data.char function called digit to int, and this one you give it a character which you know to be a digit, like maybe a 0, and it converts it into the integer corresponding value. So we convert the character 0 into the integer 0, and then we just return it. Otherwise, somebody's made a mistake and they've typed something which is not a digit. So what we're going to do in this case is we're going to have another do. We'll move on to a new line. We'll print an error message. So we'll say put stir line error invalid digit, or whatever error message you like. And then we will call ourselves recursively again. So we'll call getDigit with the same prompt. Okay, so this is a kind of more sophisticated little interactive function here. So it's taking in a prompt as an input, and then it's putting the prompt on the screen, reading a character from the keyboard. If it's a digit, we convert it to an integer and we return it. And if it's not a digit, we're going to print out an error message, and then we'll just recursively call ourselves again until the user actually puts in a valid digit. So let me make sure I save this. And I can reload it down here, make sure I actually do it properly this time. And I can try this out. I can say getDigit, getDigit. I can say enter a row number, and that's my little prompt. And if I entered a valid row number like 2, that'll be fine. So it's just returned the value true. Whereas if I say getDigit, enter a row number, and maybe I type in something wrong this time. Maybe I type the character A, and it would reject that. That's not a valid digit. If I type to B or something, that's not a valid digit. And it would only accept, or it would only terminate once I actually enter a valid digit. Okay, so that's the getDigit primitive. So now that we have implemented some I/O and board utilities, we can actually use these to implement the game itself. So let me start off by making a bit of space, and let's write a little comment so that when we look at this code later on, we know what the different components are. So now we're implementing the main NIM game. So the top level definition, which we're going to have, is a purely interactive program called NIM. So it returns a void result type. And we're going to define it by simply calling a top level function called play. And play is going to be like the main game loop that we had with the hangman example in the last lecture. So what play is going to do is you're going to give it the current board, which will be the initial board at the start, and you give it the current player, which will be initially 1, and then it's actually going to do all the actual work of implementing the game. So before we come to actually define the play function, let me just define one more little helper function which will be useful to me. Let me define a function called next, which is just going to flip between the two players. So if you're player number 1, the next player is going to be 2, and if you're player number 2, the next player is going to be 1. So next just gives you the next player based on who is currently playing. So now we can come to implement the actual main game function called play. And this takes the current board and it takes the current player, and it's actually going to run the game. And again, it's going to be a purely interactive program. It doesn't actually return any meaningful result value. We're only going to execute this function for its side effects. So I'll make a bit of space in here. This is going to be quite a few lines long, but it's all very straightforward. It's just some simple input-output stuff using all the utility functions which we have written. So I'm going to call the play function, and it's going to take a parameter which is the current board, and it's going to take the current player, and then we're going to do a bunch of things. And so I don't have to write too many spaces here. Let me just put the do over here. And what I'm going to do first of all is just keep the layout clean. I'm going to take a new line, and then I'm going to display the board so that the user can see the current state of the game. So I use my utility function called putBoard, and that will display the board for me. Now I need to do a check because the game might already be finished. So I can say if the game is finished with this particular board, so I'm using the utility function called finished, which we wrote earlier, then I'm going to end the game. So what I'm going to do actually is I'm going to take a new line again, just to keep the layout nice and clean, and I'm going to display the number, or I'm going to tell the player that they have actually won. So what I'm going to do is I'm going to emit a string and say player, and then I'm going to put the number of the player that's won, and there's a little gotcha here. If you are the current player and the board is empty, then it's the other player which actually won. So what I need to do here is if the player value here is 1, what I need to actually be printing down here is player 2. Because if I'm player 1 and the board is now empty, that means that the other player made it empty, so they are the winner. So this is the little gotcha here. I need to take the player value, I look at the next player, convert that into a string, and then print it on the screen. Okay, so when I first wrote this program, I forgot to write this part here, and of course it said that the wrong player had won. And then finally, just to complete the message here, I can do put stir line and little space here just to keep it neat and say that particular player has won. Otherwise, nobody has won at this point. So I'm going to have another do, take a new line to make things clean, and then I'm going to ask the player for what they want to do. So I'll say the player number, so they know which player is going to go. So I'll put a string out that says player, and then I'll put the player number. So put stir line, show player. So remember, show is the magic function that converts things into strings. So in this case, we are showing a player as a string. So it might print the number 1. And then I'm going to get the number of the number of the row which they wish to play on. So I'll say R comes from get digit, enter a row number. So that will prompt the player, for example, player 1, to enter which row they wish to play on. And remember our getDigit primitive, it's clever, it waits until somebody actually enters a valid digit, and it keeps looping around until someone enters a digit rather than some random character. Then I will take how many stars they wish to remove, so I can call getDigit again, enter stars to remove. So that's another prompt, and again that will loop round until they've entered an appropriate number of stars, which is actually a digit. Then I need to check, is this actually a valid move now? So I call my valid function, I pass in the current board, I pass in the row number which the player has entered, I pass in the number of stars which they're trying to remove. If that is actually a valid move, then all I need to do is call the play function, and I need to pass in a new board and a new player value. So the new board will be obtained simply by applying the move function. So the move function takes the current board, a row number, and how many stars you wish to remove. So the part in the brackets here, this part here, this will construct a new board by taking the current board and removing the appropriate number of stars from the appropriate row. And then I need to remember to flip the player. So I flip the player value, and then again, I call myself recursively. So this is an interesting little line here. What I'm doing is updating the board by actually making the move, updating the player, and then I'm calling the play function with these two new values. If the move is not valid, then I need to print some kind of error message. So I'll have a do, take a new line, make a bit of space here, print an error message, put stir ln, say error, invalid move, or something like that. So I print an error message out, and then I need to remember to keep the game going. So I call the play function recursively, and this time the board doesn't change, and the player value doesn't change because it was an invalid move. So this is just looping round here until the player actually makes a valid move. So I've typed quite a lot of stuff here, so hopefully I haven't made any mistakes. So let me save the file and let me reload it in down here, and actually it's worked. Actually, maybe let me load it up here, because now I can give you a demo and this screen's a bit bigger. So let me just clear here, GHCI, nim.hs, all loaded in, and now I can try the game and make sure it actually works like it's supposed to. So here's the game, it's printed the board, it's saying player 1, enter a row number, so maybe I play on row number 1 and I remove 4 stars, and that's worked okay. Let's enter something incorrect, let's maybe enter row number A, that's invalid. Okay, let's do a proper move now, row number 2, 4 stars, and so on and so on. So this will work now, and you could try this game out for yourself and check to see that everything actually works out, which it does. So that's it for today. It's been just a simple example of a bit of live coding, showing you how you can think about writing an interactive program by defining a bunch of helper definitions first, and then using those in a very simple way to construct a simple game. So I'll put this code online, so if you'd like to have a look at it, maybe play around with it, try and define a few things yourself, or try and modify a few things yourself, that's something which you can do. But apart from that, that's it for today, and I will see you again next time around.